Color centers. The effects known as color centers within the crystal structure of some varieties of gemstones may alter their natural color. These defects are generally introduced by extreme heat exciting and freeing electrons or by bombardment with natural or man-made radiation. Color centers fall into two categories: electron color centers and hole color centers. Purple fullerite is an example of electron color center. Fullerite is built with alternating calcium ions and fluorine ions. In its pure form, fullerite is transparent. Its purple color is caused by a color center. When fullerite is bombarded by high-energy radiation, a fluorine ion can be ejected from the crystal, creating a free space. To regain stability, it grabs an available electron close to the crystal and sticks it in the free space. The electron is held firmly in place by the surrounding positively charged calcium ions. The trapped electron is responsible for the purple color of fullerite. Smoky quartz is an example of hole color center. Irradiation of pure quartz will cause electrons to be ejected from some of the oxygen atoms. The electrons will return immediately, so the crystal is colorless. However, the addition of about 1 aluminum atom for every 10,000 silicon atoms in silicon oxide structure results in a change in the color of the crystal. The hydrogen atom present in this structure does not absorb light. Light is absorbed by aluminum oxide to produce the gray to brown to black color of smoky quartz. Color centers can be removed. The electron can only be freed from the trap when supplied with sufficient energy to move beyond the attraction of the positive ions. This can happen if the crystal is heated to a few hundred degrees Celsius. This results in bleaching of the color center. If not overheated, the color center and the color can be restored by another irradiation, and so on. Charge transfer. Sapphires are described by their very stable colors even when exposed to light and heat. Corundum or aluminum oxide crystals of gemstone quality in any color other than red are called sapphires, while red varieties are called rubies. Sapphires owe their intense colors to impurities such as titanium and iron. In sapphire, a process known as charge transfer produces the color blue. Corundum that contains a few hundredths of 1% of titanium is colorless. If a similar amount of iron is present, a very pale yellow color may be seen. If both titanium and iron impurities are present together, however, the result is a deep blue color. The process is called intervalence charge transfer, which is the transfer of an electron from one transition metal ion to another. Intervalence charge transfer is a process that produces a strong colored appearance at a low percentage of impurity. While at least 1% chromium must be present in corundum before the deep red ruby color is seen, sapphire blue is apparent with the presence of only 0.01% of titanium and iron. This energy jump is comparatively easy for electrons to achieve when light shines on the crystal. Different crystal structures. The surrounding ions of the crystal lattice create a crystal field around the transition element with an unpaired electron in its outer D shell. A system of energy levels depends on the strength and the nature of the bonding in the lattice as well as on the valence state of the transition element. These are different in every crystal. In ruby, chromium substitutes some of the aluminum ions in the aluminum oxide lattice. Energy levels available to the unpaired electrons are presented as level B, C, and D. When white light enters a ruby, yellow, green, and violet light will be absorbed by the unpaired electrons, and colors that are not absorbed determine the red color of the ruby. For emerald, which its color is also caused by a chromium impurity, the mechanism is similar, but the crystal fluid from the surrounding elements has less strength and causes a shift in absorption bands. The result is that emerald absorbs most violet and red portions of the visible light, leaving a dominant blue-green transmission.
How electrons and energy levels determine color in gemstones. The most common cause of color in gemstones is its presence of a very small amount of transition metal ion. These transition metal ions normally have an incomplete set of 3D electrons. Changes in the energy of these electrons correspond to the energy of its visible light. When white light passes through the colored gemstone and is reflected by it, some of the energy of the visible light is also absorbed, causing 3D electrons in the transition metal ion to undergo its energy change. The light that is transmitted and reflected appears colored, because those colors are corresponding to 3D electron energy transitions that have also been absorbed. Take ruby for example. In ruby, each aluminium ion and chromium ion is surrounded by 5 oxide ions in an octahedral arrangement. This arrangement splits the 5 3D orbitals of chromium into 2 sets, the dx2y2 and dz2 orbitals. These 2 sets normally have different energies. The energy difference between these sets corresponds to its energy of visible light. When white light strikes the ruby, the gem absorbs the light of energy, corresponding to the transition of an electron from the lower energy set of 3D orbitals to the higher energy set. Idiochromatic self-colored gemstones. Idiochromatic gemstones are gemstones in which the transitional metal is an essential ingredient of the chemical composition, hence why they are called self-colored. Gemstones that are self-colored have chemical constituents known as chromophores, which are key components in their physical makeup. A chromophore is a part of a molecule responsible for its color. The color arises when a molecule absorbs certain wavelengths of visible light and transmits or reflects others. The chromophore is a region in the molecule where the energy difference between 2 different molecular orbitals falls within the range of the visible spectrum. Visible light that hits the chromophore can thus be absorbed by exciting an electron from its ground state into an excited state. Idiochromatic gemstones are rare to find. Examples of these gemstones include rhodonite, azurite, and peridot. Allochromatic other colored gemstones. Allochromatic gemstones are gemstones in which the transitional metal is an impurity and not an essential component of the chemical composition. Blue sapphire is an example of an allochromatic gemstone. Its color is due to the presence of the elements titanium and iron. In the case of blue sapphire, both of them are required to give its blue color. If no impurities are present in a sapphire gem, the stone is completely without color. Differently colored sapphires in green, yellow, orange, and other shades are colored by various impurities or a combination of impurities. Most of these coloring impurities are a metal atom, so gemstones which can accommodate a variety of different metal atoms, like corundum, are often found in a large variety of possible colors and shades. Allochromatic gemstones are much more common than idiochromatic gemstones. Examples of the transitional metals found in these stones are beryllium, chromium, copper, iron, lithium, and many more elements. This explains why allochromatic gemstones are much more common, due to the large variety of transitional metals which can act as chromophores and give the gemstones their distinct color.